All right, let's see what's going on here. Is it streaming?
Oh no, that was from the earlier video.
Okay, I got you.
Sorry about that.
No, you're good. I'm just trying to.
I'll go check on my phone.
Okay. So. Let's get that out of the way. If y'all want to go ahead and get a computer that's got TIA on it, it's going to be any of the lower numbers like 1 through 10. Y'all could get a lot of stuff kind of pre-done for your lab. So if you're here, you can get a laptop, follow along with me, and then you're essentially halfway done. You want to do that, Anna?
Yeah, if you don't mind. On my phone, stop it. Yeah.
It's not showing up.
I'll see about refreshing it. I just need to refresh mine. Let's see. Thank you. Thank you so much. Midday, that video is pretty cool this weekend.
Which one was it? Oh, like there's some good stuff coming up. Okay, so it's unlisted right now, so I'm going to turn it public. That was a lab pumps and piping we're doing. All right, so let me see if this will pop up now. I just want to make sure the stream's working. Yeah, we're gonna start from scratch. Like all you need is a TIA Portal 16. Like you might have to go to start. And then start typing in Siemens. And then find TIA Portal 15.1.
That distracted us. Remember you sent me out that okay, and I completely forgot to download and have to get computers and stuff.
I'll let them do it while we're doing class. All right, so just open up TIA Portal. Y'all found one.
I got it on
Grab a laptop from 1 to 10. I want to make y'all's life easy because, like, instead of having to watch this video to do it, I'm going to let y'all do it while I'm doing it. If you're here, and cut down on some of your lap time. All right, I'm pretty sure it's streaming. I'll restart what I said there, like advanced VLCs.
10:30. 10 through like 27. Or like 11 through 27. Because you had no problem with the DC on 1 through 10. I know some of them, if
No, we're not doing deeds in here. We won't do that until 2. All right, so password is Bevel 2020. So it's student and then Bevel 2020 with a capital B.
We're making a circuit.
Yep.
The circuit.
Nope. All right. So find TIA Portal 15.1. If it's not on the desktop, go to Start, scroll down to S. Yep. And then mine's under Siemens Automation, TIA Portal 15.1. All right, so we're going to do things a little bit different than when we have when it's just me on video. We're actually going to make our program. So instead of, opening a template or whatever, go to the second thing, create new project, and create a new project. Let me know when you get to it. I'm going to go slow because I don't want to go super fast and then the computers go slow and
I was over there last time, did lab.
What, over there in the lab?
No, I was trying to do my lab on the computer over there.
Yeah.
It took me like an hour just for it to load.
The signal's not strong over there.
Not as strong as it.
do y'all have this screen right here?
I have a project view screen recently used, but we're listening. I need to create a new project.
Create new project.
That is going to be project underscore Roberts.
You don't know what it is yet? Nope. All right. So under project name, right? Is that showing up on that screen? Let's do PLC underscore ADV underscore 1 underscore your last name. Yep. All right. Now, it's going to get more complicated, but not really, because I don't want y'all constantly filling up my computers with programs, right? That's what makes them super slow. So before you come to a lab, I'm going to let the people in here do it on wherever it says for path right here. But bring a jump drive and then find it in this browse for folder and save it to that from now on. Because y'all right now, y'all need to find the same computer to be able to do. Don't toward the end. Author, yours probably says student. Put your first name dot last name. All right, and then create. All right. Once that gets done, this is portal view. And if you ever get stuck, like if you're working and you don't touch PLCs for a long time and you want to be able to remember how to do stuff, you can go step by step through here and it'll help you. Okay. It'll help you get set up in programming. The issue with that is it takes forever to do so, and we're learning how to do it, so we might as well learn it the quick way, right? This is kind of okay, I haven't done it in 10 years. I'm going to go through here, and it's going to kind of step me through stuff, but it's going to take forever, All right. Go down to project view. Portal view is more linear, where it's like, okay, you need to configure a device, and you need to do this, and you need to do that. And this is more parallel, where we can just get to things as we need them. All right, so all your programming software, like no matter the manufacturer, can program a bunch of different devices that have a bunch of different peripherals, different, speeds, different, inputs and outputs. So we have to tell the program what type of device we're programming. So if there's a function in the device that we don't have, it doesn't populate it in here, right? So go over under, like, this is the name of your project, but we need to add a PLC, so we're going to add a new device. All right, now we're going to call this ADV underscore PLC underscore 1. Okay. Now, don't click anything. I don't think you can. But under controllers, we're looking for a class 1200 controller. Under CPU, we're looking for a 1215C DC, DC, DC. Now, it's important that you pay attention to all of those, because there's 1212s, 1214s, and there's AC, DC relay, DC, 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 DC relay. Look for 1215C DC, 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 because that's the type processor that we're using. When you open that up,
I have a Symantec S7 1200.
all right, so open up that S7 1200, and then open up CPU, and you should have the whole list of the 1200 series. 1215C DC, DC, DC. All right, when you open that up, it's going to give you two different types. The main difference is the AG31 versus the AG40. We've got the newer one, the AG40. All right, if you don't know what you got,
215 AG40 OXBO.
AG4, it's the second one. No, it's
15C.
DC, DC, DC. So look under you see it now?
DC relay. Not kind of two.
Yeah. Oh my God. You know how it is.
All right, so you got
1215C, AC, DC relay, DC, DC, DC.
all right, that's the one. No, the DC, DC, DC below it. All right, now open that up and you'll see a 6E5 set or a 6E S7, some numbers, and then you'll see a 1AG40 is the second one on there, right?
Mm-hmm.
Click on it and make sure that over on the right-hand side, you got version 4.2 right there.
Mm-hmm.
Everybody cool?
Version
4.2.
I know it's right. Where does it say 4.2? I don't.
Look on the screen up there, on my screen. You see where my arrow is?
Windows not.
Okay, you probably pushed OK too quick.
It was like a very probably.
Yeah, once you get the version 4.2.
Got it on here.
You're just gonna go to that screen.
You might
It's
have,
like project.
oh, you might push enter too many times or something, like, but we'll push OK. and it should populate with your PLC in a second.
I'm doing good. Yeah, that's what mine did when it went.
All right.
That's probably.
So this right here is the name of your PLC. This is the name of your project. So my project is ADV1 Spears. My PLC is ADV PLC1. Okay. If I had peripherals that the program needed to know about, like let's say I had an extra analog output, like those little squares, like in our 1214C, it doesn't have analog outputs. So we got the signal card that goes in the middle so we could add them. The little square right there. No, like, yeah, the little square in the middle of the PLC. Nope, right there, like the square. All right, so those are called signal boards, so they can add extra functionality. We need to let the PLC know if we have one of those. We don't for the 1215Cs because we already have 2 analog outputs. We have them for the 1214s because they didn't have analog outputs. So if you do have a signal board, like you want to add functionality to it, like put it in your program too, so you have access to those peripherals. Okay. So we're good right here. Okay. Now what we need to do is up until this point in intro, you've done like Boolean things, if it's on or off. And we want to start talking about shades of gray. Okay. We want to start talking about analog values. The world is an analog place, you know, where nothing's just, you know, always yes or no. So we're going to deal with the analog inputs and outputs a lot. Like in that water trainer, we take an analog input and measure the height of that water, and then we compare it to how high we want it, and then we use an analog output to speed up or slow down that pump to compensate for the amount of water that we're losing through the drain so that we can keep it at a certain level. Cool? All right, so we need to figure out where our analog inputs and output addresses are. Okay. Like what we have to do is we need to write to the address to tell it what analog voltage or current that we want to put out, or we need to read from the address if it's an analog input. Okay. So hit device configuration underneath the PLC. So double click it, and if it doesn't come up, go down there and click properties right here at the very bottom. And that should pop up. If it doesn't, there's a little arrow over on the right. Why is my computer being slow? All right, so I might have to drag it up. You might have to drag it up too. All right, but device configuration, properties, and when you first do it, it's probably going to have all this information right here that we don't really care about yet. But we want to go down to AI2 and AQ2. What?
Here, click on, here. Right there.
There's properties, you can see what,
Oh.
there's your general IT tag system, instructions, but all right, somehow he drags his up just.
All right, so like if yours, like now that I have it dragged up, I can collapse it back and forth with this little arrow.
All right, there's a little black bar that shows up when you go down there to like, go down to like where the bottom of the confines of the box are, that's black. And then see if you get that little line that pop up. It's got
Yeah, I'll show you. You see this little arrow right here? If I go hover over that line, I can drag it up. I can click it and drag it up. Yeah. Now don't keep dragging it down because that's going to be a pain. Like now that I've got it dragged up, you see this little collapsed triangle right here? I can make it go up and down to however far I dragged it. Okay? Dragged it, dragged it. All right, so scroll down under general until you see AI2/AQ2. All right, now you see where it says analog inputs? Click on that. All right, now click on channel 0. That's going to be your first channel, and it's hard coded as IW64. A W is a word, which is a pretty big chunk of memory, because we're going to have to store 0 through, let's say, 30 something thousand. All right. And when we get a voltage on there, it's going to give us a number from, like, let's say 0 to 27,648 to represent a 0 to 10 volt signal. Okay. But it says IW64. Okay. So that's our address for that first analog input.
W is a word. What is
Input
that? Input word.
64. All right. Now check channel 1. It's going to be IW66.
I got that. I'm at
Oh, AI2, AQ2. All right, so our two analog inputs are 64 and 66, right? We need to remember that. Now, let's go down to the channel 0 for the analog output, and it's going to be QW64, and channel 1 is going to be QW66. Okay? We need to remember those. Like, if we need any information from those or to those, that's what we're going to be writing to. Okay? So, have y'all had to make a tag table yet?
I remember maybe.
Yeah.
All right, so we're going to make a tag table. Like, my PLC applications are doing the same thing right now, but that's because we're sharpening our ats. We're making our life easier in the long run. Okay, so let's go into PLC tags and add a new tag table. And it's going to say tag table _1. All right, y'all got a tag table _1? All right, so we found that the two addresses for the inputs and the outputs were 66 and 64, 64 and 66. It'd be IW for input and QW for output. Okay, like Q because they don't want you getting confused with the 0. All right, so now we're going to make a tag table to make our life easier. So scroll down over here on your PLC tags, click add new tag table, and it's going to give you a tag table _1. And it's going to have a 0 byte to represent that there's 0 things in it. Okay? Right click that tag table 1 and rename it. We want this to be special for us, so we're going to call this PLC _app _tags. If you're in advanced PLCs also, you'll be using advanced PLC tag table. If you're in applications, you'll use a PLC applications tag table. All right. Now, what this does is it gives us what's called aliases. That's what they call tags in Allen Bradley. I'm also known as this. Instead of having to remember every time I want to read from the first analog input, I need to go and find IW64. I put it in here one time and make a name that actually means something, and it's a lot easier to find. Okay, so double click on there, and we should be presented with a little spreadsheet that we can work with. All right, look.
Click it on the PLC app that we just renamed.
Yes.
It pulls up a general.
What's up, like the general name, data type, address?
Yeah. Our screen looks like this. Me and this.
Let me see.
When we click on that.
Oh, did you do PLC data? Hold up. Me. No, that's not.
We to the default tag, add new tag table. We added this. We renamed it. We clicked on
Oh, okay. I know what's going on. Like when you drag that up, like you didn't drag it back down. But instead of dragging it down, right? Click on that little triangle. Like, see, I've got this little triangle. And so when I drag it to wherever I like it, I could drag it way up here. Now I can collapse that back and forth.
Hit the screen if you flash it.
All right. So we got this. All right. Now let's name these things. All right. So the analog input, like, we could say analog N1, but the thing is, like, we're going to have to do a lot of stuff to that before we ever read from it, because it's just going to give us a number between 0 and 27,000 and some change. Okay. So let's call it, like, let's say analog underscore N underscore raw underscore 1. Okay. Because we rarely want to read that 0 to 27,648, because that, I like my in-laws. All right.
Oh, yeah.
Raw 1. Raw means that it's not in a format that is actually useful to us. Because if I was like, okay, that analog in says 10,000, well, that represents something. It represents from 0 to 10 volts, but it doesn't give us 0 to 10. It gives us 0 to 27,648, and we have to convert that to mean something to us. So we're rarely going to be just reading the analog input after we do what we do today. Okay. All right. So when I do that, go over to data type and click the little paper, and it's going to try to give you a Boolean, because that's what it's expecting you to go for first. What that's going to be is, it's going to be an integer. All right. So you can start typing in int. Integer means a whole number. Okay. All right. Now, whenever I scoot over to address, it goes red because it's in Boolean format. It's just got an I0.0, which means bit 0 of the 0 folder. So click on that little triangle, and we're going to change. All right. So it's still an input. Now it changed it to W to represent a word. Change that to 64. Okay. All right. So now we don't have to remember where that memory location is. When we want to read what the analog input 1 is, we've got a name for it. All right. Now watch this. This is fantastic. If you're doing a bunch of stuff all at once, you can iterate it, right? So if you've got a number there, Siemens is smart enough, like click on analog in raw 1. And you see that it gives me a blue box, and it gives me that little blue box down at the bottom. Hover over it, and it's going to give you a little plus sign. Drag it down once. And it incremented it. And it did go up to IW66. See, the thing is, like, a word is 2 chunks of data. So analog in raw one starts at 64, but it also has like 65 in it too. And then boom. So we've got that. A word has 2 bytes, which, you know, so you'd have 64. It just says starting address, right? So like a double, I don't know if they, like a word and a double are different in here, but in a lot of architectures, a double would have like 4, you know, like, so, you know, you couldn't, like if we wrote or read from 65, it would just be given a piece of the data for analog in1, right? All right, so we've got that taken care of. Now let's do analog out. Analog underscore out underscore raw underscore 1. All right, go ahead and push enter, and it's going to try to give us IW68 because that's the next available address for the inputs. But this is not an input, right? So we want to go and click on that, change it to an output. So we're going to change it to Q, and then we're going to change that to 64 because our first output address is 64 for our analog. And go ahead and drag that down once because we've got 2 analog outs. All right.
You might need this.
Maybe. Now let's go ahead and add our digital inputs. Okay. So let's do dig underscore in underscore 1. Push enter, and it's going to try to give us an int with the QW68. This is a Boolean, so we're going to change this. So start typing in BOOL, and then like open this up, and we're going to change this to I again, and it's going to be 0.0. All right. Dig underscore in, dig underscore in underscore 1. Yeah. So it's I 0.0. All right. So click on where it's probably still got integer right there, right? And then click on that piece of paper, and then start typing in BOO. Like backspace some. Let me come help.
There it is.
All right, so start typing in BOOL. Boolean means that it's one of 2 things: true or false, 1 or 0. Okay. All right, we have 0.0 through 0.7, and then 1.0 through 1.5. How many things is that? 0 through 7 is 8 things. 0 through 5 is 6 things. So 8 plus 6 is how much? 14 things, right? All right, so we want to add 13 new digital ends, right? So go ahead and hit that digital in, grab that little box and start dragging down. And if you look down at the bottom middle, like right now mine says 6 tags will be added. 13. Booyah. And that gets me up to 1.5. You good? All right. Now we're going to do our digital output. So do a dig in or dig out, digital out _1. When you push enter, it's going to try to give you an I1.6. That's not right. It's going to be a Q0.0. Yes, for output. All right. Now, these PLCs have 0.0 through 1.1. So that's 8, 9, 10 things. So we need to add 9. All right, so let's go ahead and add 9.
So we're gonna have 14 in total because it goes to 1.5.
No, 1.1. Oh, for digital in? Yeah. You're going to have 0 through 7, which is 8, and then 0 through 5, which is 6. So it'd be digital in 14 as the last input. And then you're going to do the same for digital out. You'll do digital out 1, change it over to Q0.0, and then drag it out so that you add 9 so you get to digital out 10. Good. All right, now one of the things about this is we've got all of our inputs and outputs taken care of now. Now that's one of the first things I ever do with the new project is I go ahead and make a tag table. I might not have everything plugged into it, and I might not ever have everything plugged into it. But now I don't have to think, what's my next thing? Like, and if I put a stop button on one of those inputs, I just go and find where that input is and change that word to, like, let's say stop button. And everywhere that I've got it in my code will change the stop button. Okay? So this saves us a lot of time because we might be using digital input 12 times. I don't want to have to, so now we've got all our inputs and outputs. All right, I made a remark that we don't want to have to remember, like, let's say that I go from 0 to 10 volts, and that's going to give me a 0 to 27,648. Well, how many volts is 10,000? I don't know. I'd have to do math, right? So we're going to make some helper functions for us, okay? Now, have y'all dealt with function blocks yet? No, not the mystery box. A function block.
No, wait, 1 second.
No. You need me to pull that back up?
No, I just went not too many, so when I tried to drag down more, it just.
Kind of messed up. While you're doing that, I'm gonna run to the restroom.
So like this, yeah. All right. Well, first class. This is first class with this. How far are we straight?
Oh, no.
This is the last one. Well, we weren't here for the last one. And we gotta do it over there too. A good thing to do.
I just gotta see it. I just gotta see it.
Yeah, that's it. Did you do all your own? Did 4 labs? I didn't. I think there were only 6. I didn't. She can have at least a 6.
No. Anyway, so, yeah.
I think she lent it out. Because I only had one and I can't find it.
Yeah.
Okay. We'll talk about it during digital.
Switch out this one.
Yeah. All right. So we're gonna go. No. All right. So if something is not in main, it does not get run. Okay? Like main is the main program. That doesn't mean that we have to put a whole bunch of random stuff in main. We can compartmentalize things, and that's a good programming habit. Okay? If there's stuff that we reuse all the time and we get it so that it works, there's no sense in building that 50 networks into main every time, because it's going to make it really hard to read. It's going to make it hard to change. Like, let's say that we made a function that multiplies 2 numbers together. And if I use that code over and over again, and then I decide that I need to make it better, if I have it in 50 different places in that main, then I'm going to have to go find everywhere that I do it, right? So we can make other function blocks to help us out here. It'll make more sense in a second. So right over main, add new block, click it. You're going to have an organization block, a function, and a data block. Not yet. Organization is stuff that like is super powerful. Main is an organization block. Okay. You have to have main, right? You can only have one main, but if you accidentally delete main, this is where you'd go back and get it. I don't know that you can delete main, but if you could, this is where you'd come back and get it. Main happens, how fast is main? It depends on how long it is. So if we have a super long program, it might take, a super long time for it to do its thing. If we have something that is dependent upon like real world timing, like we need something to happen every second, regardless of how long, we could have something like a cyclical interrupt, and that function would operate outside of main and would keep going and trigger the things that are in it every second. Okay. Or like startup. If there's something that we want to happen the first time, but it doesn't happen again, like when we first turn on the PLC, we want it to run and then never happen again, we'll put that in startup. That's important because if we had a piece of code that like initialized values to 0, it made some variable 0, every time, if we put that in main, every time I run across there, it'd be 0. So that might be something for startup. Okay. A function is a block where we can make some logic, like something happens if this happens. Okay. A data block is where we can store some information. So if we need to do math to something, we'd store that in there. Function block is the combination of those two. All right. So for right now, we're going to use function block. So click on function block real quick. Make sure language is ladder, LAD. Make sure it's on automatic. That's going to number it up. As we add more function blocks, it'll add the next one instead of us having to keep track of what it's called. Now let's change the name to let's call it analog underscore
We're adding a function block, right?
yes. So click
Analog.
Click. Underscore let's just call it scaling real quick. Okay. Cool. Analog underscore scaling. All right. Now we get something that looks like main, but it's not main. And if we do this and we run it, like we put a bunch of stuff over here, but we don't have anything in main, it's not going to get run. Okay. So you don't forget that it still has to be in main, right? Go to main real quick. All right. Make sure up top, like you see how mine says analog scaling right here. Make sure it doesn't say that. Like, so,
Main?
yes. So click main and it should say program blocks main, right?
Program blocks, analog scaling.
All right. So double click main again. All right. Make sure it says program blocks main. We want to make sure whatever we put in that function block, it gets run when we run. So go over and click, like drag, don't click it, just drag analog scaling into here.
Into main?
Yes. It's going to ask you for a call option and it's going to say a single instance. That's going to give it a data block to keep track of all the stuff that we're going to do in there. We just made a block. You know how they have those functions like with the mystery bots and all that crap? We could make any of our functions from scratch by doing this, right? We just made a box that does whatever we want it to do, okay? Now, this doesn't look that amazing because we don't have anything in analog scaling now, but imagine that we have 50 lines of code and we got it perfect and we needed to use it over and over again. We could just drag it in wherever we needed it and it's not going to clutter up main. And if there's a problem, it's probably going to be main because we're going to double check once we do this that works. And if it works, like if our function block works, then we don't have to change that and we don't have to troubleshoot that anymore, right? All right, so let's go back into analog scaling. All right, so analog scaling now has two things, a FB1 and a DB1. We want the function block one. DB1 is where it's going to keep track of all of our data, okay? Now imagine I made a function and wanted to give it to you. I wouldn't give you all a main, I would give you that function block so that you could put it in your main, okay? What's our problem? Like, what's the solution? Like, what's the problem that we're trying to make a solution from? We're going to have a real world thing give us 0 to 10 volts, and we want that to represent something, right? It could be an angle. We could put a knob on something, and as it turns, like we could say, okay, wherever it is right now equals 0 degrees, and then turn it to 90 degrees and say wherever it is right now equals 90 degrees. And then we could scale that so that by, turning that, it's giving us a 0 to 10 volts, but we don't really care about the voltage in that point, right? Also, we've got an analog input that's not going to give us a voltage. It's reading a voltage, but it's going to give us something between 0 and 27,648, which means nothing to us right now, right? So let's go ahead and convert that to something that does mean something to us, okay? So I want you to drag 2 mystery boxes down. Click on the question marks on the first one and start typing out norm, N-O-R-M, and you'll see something called norm underscore x. Click that. And then in the second one, start typing out scale. And click that. So now we've got a normalization function and a scaling function. Okay? We're going to use these a bunch. All right? So what normalization does is it takes any 3 numbers. And it gives you a number between 0 and 1 that represents those 3 numbers. Okay? If I gave you 0, 100, and 100, like, so 100 is the variable, and it's in between 0 and 100 is the minimum and the maximum. What percentage would that be? What would 100 be out of 0 to 100? 100%, right? So it would give you 1. Like, all right, it'll give you a whole number 1. All right, let's say I gave you a minimum of 0, a maximum of 100, and my variable was 50%. So it's going to give you a 0.5. It's from 0 to 1. And that's magical because all I have to do is on the opposite side of things, I just need to find the 50% of whatever. What I'm doing is multiplying by that 0.5. So normalization takes whatever range you're talking about and scales it into what you could think of as a percentage, because it's 0 to 1, and that's going to give us a multiplier, right, to represent how much of the whole that variable is. Okay? So if I had a minimum of 0, a maximum of 100, and I gave you 25, it'd be 0.25, right? And then if I wanted to scale that between 0 and 200, right, then I would just multiply that 0.25 times that 200, get 50, so 50 would be the same proportion in the other, okay? So that's going to take things from one range into another, okay? So our first range is going to be 0 as our minimum and 27,648 as our max, okay? Our value is going to be our analog in raw 1, okay? So that's taking an integer, a whole number, and it's going to give us something between 0 and 1. Now, that little factor is not something we'll have to use ever again, okay? So we're just going to kind of give it a throwaway variable. So we're going to call this raw underscore in underscore 1 underscore normd. I did mystery boxes, and then I started typing in NOR and then SC.
Minimum is 0. I put 0, but it won't.
It gives you a red. It's going to give you a red until it knows what data type it is. But once you put in the analog in1, and that's an integer, then it's going to it's going to turn blue.
Alright, so we put analog integer 0.
Analog in raw 1 as the value. So minimum is just 0, and max is 27,648.
So like this.
Yes, and it's gonna stay red until you put that value in, which is gonna be our variable analog and raw one.
Oh, okay.
Because they all have to match. If I'm comparing an integer to a real, which is a decimal, they're not gonna match. Because one integer is not equal to 1.0. Like, they're just not. Okay?
I only have analog scaling on here.
You only have what?
When I go to the output, the analog integer in there, I only have analog scaling.
Good stuff.
Wait. Oh, have you done the value yet on the left side?
Got a question mark right there.
Oh, analog integer.
Analog.
In raw one.
That's my mistake. Now I understand.
All right. Now, I put in raw underscore in underscore one underscore normed, but that's not a variable yet. I need to give it memory. So I'm going to right click it and define that tag. And it's going to be a global memory data type real. Okay. A real number is a real number, a decimal number. Okay. Real numbers are huge. Even if we're only going from 0 to 1, there's like an infinite number of numbers in there. Now, you know, I don't know if I think it's a long reel, which would be even higher precision. The problem with that is, well, it'd be probably a double, like where, like, if I'd have an overflow at like a certain decimal places, I can get more precise with a long reel. I think that's what the L reel is.
Global memory, you have local out, local in, local static. That's so there's just different types of
Yeah, like so local means that it doesn't go out of here. Well, a local in and a local out. You know how on a function block sometimes you have inputs and outputs that you can make the you can change, like this little box right here, this norm. We can make our box that's in main in here so that we can add numbers to it and then it'd go into here. Right? We'll get to that. All right, so not today, but
there's a lot.
all right, so this is going to be global memory. Real. Define that. All right. And then instead of having to type that all out, like since I need to put that output into the value of scalelets, if you hold control and drag a variable, it's going to make a copy of that variable that you can take over there.
Control X.
No, just control and then drag it. Or you can start typing it in if you want to. All right, now on here, we need to decide what we want that to be. If that input was going to represent a temperature, like that input was going to give us a 0 to 10 volt signal representing 0 to 100 degrees, then we might put 0 to 100 right here and then put degrees right here, and that would be what it is. We don't know what the input's going to give us yet. So what we're going to do is we're going to do a 0.0 because we're going to do a real on this to a 10.0 or a 10.0. Reason we're doing that is because if we just do a integer right here, then it'd be, what's the difference between 1.1 and 1.2? We might want to know that difference, right? We don't want it to just jump from 0 to 1 to 2 to 3 to 4, right? All right, and then our output, we're going to call this analog underscore n 1 underscore volts. Okay, so that's taking it from 1, and let's define that as a real. So global memory and real. Now that's going to blue everything out. Like, so Normet should take an integer into a real, and then Skillets will take a real into another real. So all this does is it converts that count number into a voltage that we recognize. Okay? Now, what if we want to use that on either analog input? What if we want to use that on like any input? We hard coded that analog in raw 1 to that value, right? Correct? So every time this runs, it's just going to convert that over to whatever we said. What if we wanted to make this a more general purpose block, right? We're going to convert something into 0 to 10. Instead of just doing a variable that stays the same, let's do a local in. Okay, so click on the analog in raw. Now when this runs, it would convert that raw into the analog in 1 volts, right? But let's say that we don't know what analog input we want to use. Okay, so let's call this analog what?
I apologize. I didn't catch what we defined that, volts at.
As a global memory and a real.
I apologize.
No, you're good. All right, so what we're doing now is we're going to ignore the static coded variable, right? We're going to make it so, like, right now we've just got a box in there, like in main, but we're going to make that box in main more functional. Okay. So what we're going to do is we're going to make a variable called analog underscore in just by itself. Now don't click enter because it's going to try to give you one of these. Click outside of it and it's going to give you the red squiggly lines, right? All right, now right click that and define it, but instead of doing a global memory, let's do a local in, okay? Local in. Now notice something. It doesn't give us an address, does it? That's because it's not going to use an address. It's going to ask us for what we want to put in there later. Okay? So we're making this function block even more functional by not hard coding certain things. Okay? So just go local in, make sure it's an integer. Booyah. Now we've got a hashtag, and it's not even in our tag tables. It's up here in our local variables. Okay. Now watch this. Go over here to analog in 1 volts, and we're going to say analog underscore out underscore voltage. All right. Right click that, define that as a local out. And it's going to be data type real. All right, now go ahead and save the project. I've got a court meeting on Zoom for my nephew at 1:30. All right, so I'm going to call this a little early, but what y'all are going to do for your lab is I want you to all make this, and then I'm going to give you a like Advanced PLCs is making little potentiometers so that you can get 0 to 10 volts. All right. What you're going, y'all, the people who came today are going to be way far ahead because all you got to do is put that on and then verify that it works. All right. When we go back to main, we're going to have a red function block because that function block does not represent what's in that function anymore. Okay. Local out, local out. Just go up to save project, and it should save it as PLC at advanced 1 underscore your last name. Yes.
You want to go back to that, where we had the,
This.
yes, I just need to see, out. Okay.
All right, but that's a local out, and it's going to give you a hashtag because it doesn't have memory yet. We have to give it memory when we use it.
Still in a box. It's a hashtag. No, actually. I'm in a box.
All right, go to main. Let's see how we are here. We've got red all over that thing. That says that this box does not represent what's in that function anymore. Because beforehand, we didn't have any inputs or outputs. We want to make that function block more functional so that we could use it over and over again, right? So right click that and go down to where it says update block call. And it's going to show you the difference, right? So I click OK, and now I've got an analog in and an analog out voltage, right? And instead of it being hard coded to that analog in 1, I could put analog in 2 right here, or analog in raw 2, right? And then now I'll get an analog out voltage that I could put into any variable I want. So I'm not tied to just the analog raw 1. Right? And I could use this over and over again. I can go and I can pull this into here, and it's going to give me another data block because it's going to be doing more math, right? And I could do analog in raw 1. Cool. Now, that doesn't look that amazing because we only did like 1 line of code in there, but imagine it's 5 lines of code. I'd be doing 5 lines of code every time to replicate that, right? But now I can make sure that that works once, and then now I can reuse it all the time, right? So what I want y'all to do in lab is to make this, then I'll give you a 0 to 10 volt potentiometer, and you'll put in there and verify that that's coming out, right? Cool, as a voltage. And if you want to change it, like you can take this bots and we could copy it and then make it like 0 to 60 hertz or something, right? And we could say frequency in or whatever. Okay. So the only thing that I think is going to cause us problems is we hard coded this raw N1 normed, right? So what we probably need to do is let's do a normed. Let's just say normed right there, right? It's going to give us a red. Let's define that tag, and let's call it a local temporary.
I got it as norm, raw and one norm.
Yeah, so just change it to normed, because like since we have that hard coded, what's going to happen is both those function blocks are going to be changing that normed value, right? So we're using a temporary place to just get it from X to, or from this position to this position, right? So we'll Control Z that. And now we should be able to use this over and over again on any input and take it from 0 to 27,648 to 0 to 10. Okay? Now, keep this, like keep it saved, because it's very important that, because we're going to build on this. Okay?
I'm going to get a flash drive, like, as soon as we finish here.
Okay, so go ahead and save it on there too. Now, when you save it on the flash drive, look at, like, mine saved on the desktop. All right, I don't want you saving on the desktop, but you see this PLC app 1? Like, a lot of people will be trying to go into there and saving this. You need all of that information. So what I need you to do is right-click that whole folder, and then, or move that whole folder into your flash drive, or it will say corrupted, right? If you just,
Save project.
We need to say the main of you want to.
no, everything's like when you're in that project, it saves everything. All right. And then wherever you saved it to, most of the time it's the desktop, you want this whole folder to save on your jump drive. Because if you just save some of this, like if you go into that folder and try to save this right here, it won't let you open it. It needs all of these files in there to actually work. Okay? So you'll drag that into your jump drive. All right, so I'm going to go get on that Zoom call. Okay? Wish me luck. He's a sweet little baby who hopefully is coming home with us. If you're in digital, it might be a few minutes before I get off of there at 2. Just let everybody know that I'm raring for digital, because digital is my favorite thing, right? But you know, family is my most important thing. So let me get in there real quick, and then yeah, I'm doing all of them today.